Hello everyone, my name is Xintong, and my project for RIS 2026 is Preference-Aligned Latent-Space Safe Control. So let me briefly introduce latent safety filter first. A safety filter is just something that corrects you when you're about to fail. For example, if you ask a robot arm to pick up a full bag of Skittles, then the safety filter will correct the robot with a safe action whenever it's proposing an unsafe action that will cause the Skittle to spill. And the latent safety filter just adds onto that by allowing the safety filter to use high-dimensional observation directly, such as RGB images, without requiring low-level physical dynamics of the environment. So the open problem in this field is that current safety filters are not aligned to human preferences. The limitation is that traditional latent safety filters classify every state into either safe or unsafe. They only focus on whether failure is avoided, but not how. But in real life, real humans have more nuanced preferences about how they think both the failure and safe scenarios should be handled. There are multiple ways to avoid failure and also multiple ways to fail. So when safety can't be guaranteed, then the human user will want the safety intervention method to be the most desired one. And when failure is inevitable, which means there's no possible safe actions, then the human user would want the policy, the safety filter, to minimize the impact of failure. So in this example below, the robot is proposing a safety intervention that will cause the egg to safely land in this plate, but it's sunny side down. But the user, the lady below, might prefer the egg to actually be sunny side up. So there's a discrepancy between what the robot think is good enough, which is safe, versus what the human user actually wants. So there's an upgrade that can be solved. So our project goal is to close this gap by developing a latent safety filter that is aligned with user preferences in both the safe and unsafe scenarios. Our method is two-part. Offline, we learn a preference-aligned safety margin from relative preference labels. For example, the one shown below is showing an egg sunny side up is better than an egg sunny side down. And we use a Bradley-Terry loss shown in the below equation to update the model. At runtime, we use this trained preference-aligned safety margin to filter the actions, so that the filtered actions not only align to binary safe-fail classification, but also align to the user's preferences. We did a proof of concept simple simulation experiment in a Dubin's car 3D toy environment. We can see that when failure is inevitable, shown in the upper row of GIFs, the two cars choose different way to fail according to their own preferences. And when in safe regions, the two cars choose to stay in their favorite safe regions, and both preference sets are developed by us, designed by us before any training. So this example showcased that in a simple controlled environment, when given preferences, the trained failure margin can represent different preferences of different users, and also the learned safety filter can act according to the preferences and be safe, and fail in the most desired ways. We then moved on to a hardware experiment of egg cooking. In this environment, the robot arm is expected to move an egg from the pan to a plate with a flipper. We designed more nuanced preference sets, including state-level preferences such as where the egg should be when it's moved into the plate, and also in what manner should the flipper drop the egg onto the plate, and also how the flipper should move during the motion. We also designed different preferred failure modes. For example, some user may prefer the egg flipped on the plate so that it doesn't get the table dirty, Or some user may prefer the egg to be fallen on the table instead of flipped on the plate so that the egg yolk can be preserved. We trained two failure margins with two opposite preference sets, and we did full trajectory rollouts with the trained failure margin values. So the two lines, the blue and red lines below, show the trend values of the two different failure margins. We can see that during the rollout, they have different values regarding to the same frames according to their different preferences. And also at the end, when the egg is flipped on the plate, they have different preferences about how the egg should be flipped on the plate. So they assign different values to this outcome. This is another example showing a worse failure that the egg is flipped on the table, and both trend failure margins assign very low value to this failure, which means they're able to rank both failure modes and safe modes. Some limitations of our work is that most preferences remain state level, and we only do state level analysis. Even for preferences that are supposed to be trajectory level, such as flipper motion, speed, and steadiness, we only use short clips to analyze this feature without looking at the whole trajectory. The second one is that our intervention threshold determination is still a heuristic process, which means we just do a threshold sweep, testing different threshold and seeing what they do on the performance of the safety filter, instead of actually doing careful calculation of what the threshold should be. Lastly, the learned safety value preference values are sometimes not ranked in the correct way. For example, sometimes safe states have even less preference value than the failure states. Future work immediately is to first to test safety filtering out the egg experiment. Since we already have two trained failure margins, we can just train in a downstream reinforcement learning policy and then run the safety filter on that. The second one corresponds to the second limitation I just talked about. We need to do conformal prediction for threshold calibration. This method guarantees a certain recall rate for the safety filter so that we can determine computationally what the threshold should be. And the last one is something that we wish to do in the near future, which is to represent preferences with language instead of relative preference labels. Thank you for watching and hearing about my work.